In this episode, geography professor Dr. Hester Giscout discusses a hot topic, glaciers. Glaciers are cool, and glaciologists have been examining them for more than 200 years. However, recent global climate change patterns have rapidly overheated glaciers, resulting in widespread glacial retreat and even the disappearance of glaciers. Dr. Giscout will highlight some of her main research results, including insights into processes on, under, in front of, and around glaciers, ice flow instabilities, and new techniques that she has helped to develop.
I have not been to a glacier in the southern hemisphere. I've only been to glaciers in the northern hemisphere. And if you want to go to some glaciers just across the border here, you have to be there within the next 25 years, because otherwise they'll be gone. Same thing for glaciers in the tropical regions. So, okay. Okay. Glaciers are the best climate indicators in the world. So I'll talk in this talk about glaciers, the connection with the climate, what the climate does to the glaciers, what the glaciers do to the climate, and why glaciers are reacting in different ways to this climate. So what is a glacier? A glacier is a mass of perennial ice and snow that moves. And it moves because gravity is pulling at it. There's no giant pushing or pulling at it. It's just gravitational flow, and it flows a little bit like a frozen river. It's a viscoplastic material, so it's not exactly like a liquid. It can break too, and you can fall in the crevasse when it's broken. And all glaciers are either completely or partly on land. So sea ice or ice on a lake is not a glacier. Here you see two examples of glaciers, one in South America, part of the North Patagonian ice sheet. That particular glacier is a couple of 100 kilometers large. And what you can see here, it retreats and it formed a lake in front of it. And that's what's happening now a lot around the world, that these lakes are actually like speeding up some of the retreat of the ice because suddenly there's icebergs that are calving into these lakes. On the right, you see a small glacier in the Canadian Rockies, and what you can also see is the glacier tongue that is sticking out is darker than the upper part of the glacier, where the snow line, the snow of the previous winter is still remaining by the end of the summer. So why care about glaciers, right? Clearly, I'm a glaciologist, I care about them, but why should you care about them? We can extract ice cores from the ice sheets, and these ice cores are actually the best climate records in the world. We have annual layers of not just temperature and precipitation, but also all the atmospheric chemistry that we have. So we have a baseline of the natural fluctuation of all these factors, and then we can compare that to what we are doing to the atmosphere. And even our atomic weapon kind of race and like some nuclear bomb testing ends up in these ice cores. So nothing is secret for these ice cores. Okay? At the same time, these big ice sheets and small glaciers are climate regulators. You can imagine if an ice sheet grows, it forms a mountain. That mountain will then change the whole atmospheric circulation, and when it melts into the ocean, it will also change the ocean circulation. Now, glaciers are generally white, so where you have a glacier, it reflects more of the solar radiation. So it, in fact, keeps the Earth cooler, and it keeps themselves cooler. They're also the best climate thermometers, because if you have a warmer climate or more solar radiation, they obviously will shrink. So they're actually shrinking, and they're one of the earliest climate indicators that we had. Our landscape here in southern Alberta, the top 20 meters of it is completely formed by the glaciers, either by eroding coulees in terms of outburst floods, or by bringing some foreign rocks, like the Okotoks Big Rock, to our environment. And glaciers and ice sheets, on the one hand, erode the terrain, then they transport all that material long distances, sometimes thousands of kilometers, and then they dump that material, sometimes in neat ridges, but sometimes in like more hummocky kind of rolling terrain like we have when you drive to the airport here. Most of you will have been to Okotoks, the big rock that was eroded from Mount Edith Cavell, close to Jasper. So it was like a rock slide that fell onto that ice sheet, and that was brought down about 500 kilometers to Okotoks. We can use some of the sediments that we have from these glaciers, so it's actually a resource for us. If you walk around campus of the University of Lethbridge, all the nice red rocks, they're all glacial erratics that were eroded from the Canadian Shield. What we can also use of glaciers are the best kind of water, the large water towers that we have. About 75% of all the fresh water in the world is actually frozen in these ice sheets. So a lot of the water in some of the rivers in BC and Alberta comes from glaciers. In the late summer, that can be up to 50, 60%. So we have on Earth a limited amount of water. We don't get pockets of water from outer space, or we don't lose any water. So if we have more water frozen on land, then the sea level is lower. If the glaciers are melting, then the sea levels are rising. So we can actually see that balance going on. In some countries, we use the water for hydropower, and in BC, there are some hydropower plants that are actually dependent on the meltwater that comes off these glaciers. The glaciers also keep the water cool, so there are certain types of fish, salmonoid fish, that are actually dependent on the oxygen-rich, very cold waters. Along the coast of Alaska, you can actually see a lot of sediment that was eroded from beneath the glaciers, and that attracts krill, and that attracts fish, and then the fish attract the larger mammals. So there's the whole trophic system that is actually dependent on the glaciers eroding and freeing up all these nutrients. But glaciers are sometimes not so good. Sometimes they actually are correlated with glacial outburst floods or big landslides. And these glacier hazards, we need glaciologists to be able to predict when the hazards are occurring and how far from the villages these things are happening. So now we actually skipped one. So if we have glaciers on Earth, and we know about the landforms that are formed from these glaciers on Earth, we can also recognize on other planets whether there were glaciers in the past or whether there still are glaciers. And the good thing about finding glaciers on other planets is then the likelihood that there is water on these planets is so much higher. And when there's water on other planets, the likelihood that there's life is so much higher. So not just planets, but all planetary bodies that are fairly cold have some frozen systems, and a lot of glaciologists work on those planetary bodies too, to understand what the glaciers are doing there. So this is Mars. Mars has a North Polar and a South Polar ice cap. It also has seasons where these ice caps are actually growing. But Mars doesn't have water ice. It's actually frozen CO2 right now. It has some water underneath in the sediments. And finally, if you haven't seen a glacier, glaciers are beautiful. Most people that go to Banff National Park or Jasper National Park come there because of the pristine mountains and the glaciers. So that's why you should care about glaciers. So now, how do they work? And how many are there? So you can find glaciers in the high mountain regions and the high Arctic regions, so very cold regions that have snowfall, and the snow remains for years and years and years. And right now, we can count all the glaciers in the world, and there's about 215,000 glaciers in the world. Now, there's only about 2,000 glaciologists, so we cannot visit every single glacier and do fieldwork on these glaciers. So as a glaciologist, we use a lot of remote sensing and computer modeling to try and understand these glaciers and measure them. So apart from these smaller glaciers, we also have two ice sheets, the Greenland and the Antarctic ice sheets. They're clearly like closer to the poles. The Antarctic ice sheet is so big that if it were to melt completely, it would raise the sea level the global sea level by 60 meters. Now that won't actually happen from one day to the other. That actually takes thousands of years, at least 5 to 10,000 years or even more for the big ice sheets. But there is a lot of water available there, so when it starts to melt, it may contribute more than all the small glaciers in the world that only contribute about half a meter if they all melt completely. Then the Greenland ice sheet, there can be 7 meters from this particular ice sheet when it completely melts. And again, that takes thousands of years, at least 5 to 10,000 years. So at present, with our present climate, we have about 11% of the Earth's surface covered by ice, but in the last ice age, we had about 30% of the Earth's surface covered by ice. And here in Lethbridge, we had about 1.5 kilometers or a mile, if you're like of the old system, of ice above us. And at that time, there was so much frozen water on land that the sea levels were about 125 meters lower. So you could walk from France to England, you could walk from Siberia to North America. So talking about sea level, I am from the Netherlands. I was born half a meter below sea level, so there's a reason why I'm here, and I'm also on the podium. I'm like, I will get wet feet a little bit later than you have. I saw my first glacier in the European Alps when I was 16. And it was pretty impressive in a way, but I thought glaciers were more like blue or white, and I didn't realize they were actually so dirty. I started to appreciate that a lot later. So this is Glacier du Trian with me in front of it, being sweet 16. Since then, I have been to a lot of glaciers in the Northern Hemisphere, and I do glaciology using a lot of different techniques, so both going out in the field, and that's where you see all the pretty pictures from, but also I use remote sensing and satellite imagery, that's the same thing, and computer models, and I data mine some of my data. So there's other people that have collected the data that use it for a certain purpose, and then I actually look at that again, because we are collecting so much data. We collect more data than we actually analyze. So it's really important to go back to the data that was collected in the 1950s, 60s, and look at it again with new techniques. So here you see a world map with some of the areas that I have been doing research in. A lot of these are in the Arctic regions, and I like being cold, and I like to suffer in the field. So I basically now bring students, and I have the students suffer with me. So these are just 3 examples of some groups of students that I've taken in the field. This is on a glacier in the Canadian Rockies, the Shackleton Glacier, where we had to helicopter from Golden to the glacier. And then you're there for 3 weeks, 24/7 all together. And I teach them about glaciology in challenging environments. And I don't only teach them about glaciology, but also about the scientific techniques, the processes, how to survive in like extreme environments, how to jump crevasses, how to not jump crevasses. I've never lost a student or had any student injured. And in the end of the day, after a long day on a glacier, your day is not gone. You go back to the beautiful hotel, and you have to cook your meal. You have to stave off the bears. There's like a little bear fence over there, and you are looking forward to the next day where you can tend to your blisters again. So glaciology is not just the study of glaciers, it's actually the study of all snow and ice. So there's actually a table over there that is the grad students of my colleague that studies permafrost, so the frozen ground. It's also a glaciology study area, but also like people that study snow avalanches or sea ice or lake ice, they're also glaciologists. Glaciology is a branch of earth and planetary science, and in any science you can have some of the research that is more applied and some of the research that is more pure or fundamental. So the applied research basically wants to know what the utility is, so kind of how useful is that for people. So in terms of glaciology, you can ask yourself some questions. how much will global sea level rise? How much water will there be in our rivers? Will this snow avalanche reach the road or not? So those are like applied questions. But we also, as glaciologists, have a lot of interesting fundamental questions. So first of all, how do glaciers flow? What are the different crystal types? What was the fluctuation of a certain chemical in the atmosphere in the past? There's maybe not exactly applied, but I must say, these fundamental and applied sciences, they're not really opposite. So you can actually look at it in a different type of paradigm. And this paradigm is where, oh, I see it now. I don't know, I didn't put that back. There we are. Okay, so what you see here is there's 4 axes. The bottom axis is the fundamental one, and the right axis the applied one. You see that they're not opposite axes on this particular graph. Then we have curiosity-driven research and pragmatic research. Now, I've put like famous scientists in each of the corners. So one is an inventor, more of an engineer, Thomas Edison. Albert Einstein is more of a pure like physics. Louis Pasteur is more in the health sciences, experiments, and then Carl Linnaeus classified the plants. But apparently half of Canadians cannot actually mention any female scientists. So I have given here some female scientists. Now, most of you will know Marie Curie, and that's where it stops, okay? But actually, under Marie Curie, there's 2 of the scientists that work at the University of Lethbridge that are in that corner, Gerlinde Metz and Olga Kovalchuk. Now, in the top left, you see Hope Johnson, and she actually received an honorary doctorate from the University of Lethbridge. She classified the bones of dinosaurs, and from that, we actually learned a lot of different things. The woman below her, Annie Cannon, she classified the stars, and it's still the Harvard classification of all the stars in the world. So there's each of these corners, all the 3 people in the bottom left, they're kind of the contemporary Einsteins, although the middle one just died. The bottom one just got the Nobel Prize for mathematics just yesterday. And in the top right, you can see a Canadian that also got the Nobel Prize for physics. And she's more in the engineering part of physics. So my work, if I actually look at my papers, if I strictly, I basically want to say, yes, we classify these people in all these different corners, but maybe it's not really true. Maybe they also actually looked at science from different standpoints. So strictly speaking, I just picked 4 of my papers and I just put them in the corners where most of the work was from. But each of these papers actually borrows from some of the other fields in science. And I must say, when we classify anything that you classify as a human weakness, nature is a continuum. So when you actually see these classifications of applied and fundamental science, it's flawed, as well as some of the funding that goes to these sciences. So applied science tends to get more funding because industry is more interested in it, but you always need the fundamental science too. Okay? So now let's go back to glaciers and why some fundamental science can be applied. I told you there was about 215,000 glaciers in the world. Now, only in 2014 were we able, as a collective of 65 researchers, this is a paper with 65 researchers where I'm one of the co-authors on, we were for the first time be able to map all these glaciers. So we now have a computer map, an outline of each of these glaciers with characteristics of these glaciers. Now, by itself, it's not that useful, but it becomes useful when, on the top right, you see actually that the the Times World Atlas actually made a glacier map. I don't know if you remember 2012, and they chopped off a large part of East Greenland, where I had done my entire PhD research. So they had 500,000 square kilometer of glaciers chopped off. So on the bottom right, you see the image where you can actually see in the gray the outline what Times World Atlas had, and then my glaciers on top. So then it becomes useful to correct some of the mappers that are not glaciologists. They had taken perfectly correct data set, but they actually put the 500-meter depth line of an ice sheet as the edge of the ice sheet. Okay? And then we actually corrected them immediately. Initially, they didn't want to admit even they were wrong. We're the Times World Atlas. We're never wrong. Okay? But I could say, like, I have all my glaciers there. And eventually, they corrected it with the help of like the glaciologists that were able to tell them exactly where the glaciers were. The other thing is, if they had chopped off that part of the glaciers, the sea level would have risen by more than 2 meters. And clearly, the sea level had not risen by more than 2 meters. So you always can do like a back of an envelope calculation if you know something about the system. And that is important. You need experts that know about the system, that know that, oh, if this is wrong, then this, or if this happens here, then this must be the result. And if I don't have a result, there must be something wrong with my calculation, for example. Okay, so that is science correcting. So let's go back to my first glacier. As all tourists, I actually took the top photo in 1985 from like a particular rock, and then I found a photo online in 2004 where you also see the same glacier, but now there's a yellow line that indicates where the glacier ends. If I draw that same yellow line on my photograph and then calculate how much that particular glacier retreated, it retreated 700 meters in 19 years. Now, my first response was, I'm getting old, even though I wasn't getting old that much. My second response was even more scary, and that was, things are going much faster than even the glaciologists thought. So the retreat, 37 meters a year of this particular glacier is really fast. And if you put this into like a longer term perspective, so from 1880, this is the Swiss that actually like make watches and like to measure things. So they're very good at measuring all these glaciers from year to year. They've like walked their cows with the bells up, and they actually had like rocks to indicate, okay, the glacier's here on this year, and then came back the next year. So we have a very long record in Switzerland and in Iceland. These are two regions where we have that. So we can actually see the blue is where it advanced, where it was a little cooler climate. The orange is where it retreated, and then the line is the cumulative retreat. So it retreated more than a kilometer, 1.2 kilometers. So on average, the retreat was 8 meters a year over this entire period from 1880 to 2017. Now, in the last period, kind of from when I saw it, the retreat has been accelerating. Now, I can draw this graph for almost every glacier in the world, and it will tell you the same, like accelerated retreat since 1985. And this means that the glaciers are losing mass more rapidly now than ever before. And where is that water going? That water is actually going into the oceans. First into our rivers and then into the oceans. So, this is a really tricky one. Okay. How do glaciers work? Okay, so to understand why the glaciers are advancing or retreating, you need to know why there are glaciers in the first place. Well, it's winter right now. The entire mountain is frozen over and like snowed over. But by the end of the summer, you see the snow line retreat to higher regions. So what you see on a glacier is when you visit a glacier in the end of the summer, that's usually about September, there is a region where there's still the snow remaining from the winter before, and that's called the accumulation zone, mostly fed by snowfall. And then below the snow line, so in the lower elevations, we actually have the bare glacier ice exposed. That's called the ablation zone. And in the ablation zone, over an entire year, there's more melt and more icebergs calving than accumulation. So clearly in winter, there's some snowfall, but in summer, there's more melt than the snow that fell in winter. Now in the accumulation zone, we have more snowfall than melt over an entire year. You can have some melt, but it's so little that only maybe half of the total amount of snow that fell remains there. So if this happens on a glacier system, what do you think will happen? The accumulation zone will get higher and higher and higher. The ablation zone will get smaller and smaller and smaller. And we have these towers of ice. So what a glacier does is redistribute this mass by flowing. And glaciers that have more snowfall will flow faster to redistribute that mass than glaciers that have less snowfall. So closer to the coast, like, you know, it's pretty wet in Vancouver. So if you go a little bit higher to the coastal mountains, you have a lot of snowfall. The glaciers are flowing slightly faster than in the Rocky Mountains on the lee side of the mountains there. So as a glaciologist, you can actually measure these things. And annually, we can actually look at this as a mass balance. It's the same as your bank account. You can put money in, you can take money out. If you put more money in over a year than you take out, well, it's growing, right? So that's what we call a positive mass balance. When it's growing, the glacier will get longer and thicker. If we take more money out, the bank account, you're in the red. So you may have shrunk completely away, weathered away, and that's what glaciers do too. So they respond to that mass balance. Now, strictly speaking, if you want to measure this in the field, it's very labor intensive. In the accumulation zone, you have to dig a snow pit. You have to kind of measure exactly how much water equivalent there is in there, because there's some more fluffy snow and some dense snow. So we translate that to how much water there is, and that's called water equivalent. You'll see that come back. Now, what you see in the center here, we also drill ablation stakes in the ablation zone. So you basically drill a hole and you put like a bamboo stake in there, sometimes several bamboo stakes strung together. You drill it in and it sticks out this much above the ice surface, then the ice surface is melting, and then you come back, and what you see here, I'm measuring all the bamboo stakes. Like here, there was like 4 meters of melt in a year of that particular glacier. So that's kind of the common melt rate in the ablation zone in the Canadian Rockies, 3 or 4 meters a year of melt. So these like ice tongues are getting thinner and thinner and thinner. You can also do something where you don't have to go on the glacier. So this is called the hydro budget method. It's still like cold. I'm standing in the river, but basically all the melt water that comes off that glacier is ablation. So if I can then calculate how much snowfall I have that budget. So from that we can then figure out how fast the glaciers are flowing. Now in the Canadian Rockies and in the European Alps, for example, ice flow is generally not that much faster than about 100 meters a year, apart from in ice falls. So you see a map here where we've measured the ice flow from satellite images, but I've also measured the ice flow from these same bamboo stakes. So I put them in, and then the next year they are like 30 meters further or 100 meters further, and I can compare the satellite imagery with the ground truth, like the proper velocities, and see if the satellite is actually doing a good job, or if my interpretation of the satellite is doing a good job. Now the big ice sheets have like flowing, like outlet glaciers and ice streams that flow several kilometers a year. The fastest flowing glacier, permanently flowing glacier, is flowing 16 kilometers a year. So you can almost sit there with your launcher and see it like flow past, okay? These glaciers in the Rockies, no, I wouldn't sit there with the launcher. The grizzly bears will come and visit you before you've seen anything. So apart from measuring it in the field and like doing really labor-intensive research on one particular glacier, we can also understand the processes, and when we understand the processes, we can put that information in computer models. So one of the important processes is melt, and melt is not just from the warmer temperatures, but it's also from the solar radiation that's coming in. Some of that is reflected. It's also coming from the long-wave radiation that is actually, like, the more moist the air is and the more clouds there are, you know, when it's a cloudy night, it's often a warmer night than when it's a clear night, so that actually traps some of the long-wave radiation. You can also get long-wave radiation from valley walls that are rock walls that clearly warmed up more than the glacier surface, so the ice close to the valley walls will actually get some of that to melt extra snow and ice surface. And then we have some exchanges that are dependent on how high the temperature is, how much wind speed we have, and the moisture differences. So what you see on the left here is like an energy balance station where we actually measure each of these components. Now, if I do that in a couple of locations on the glacier, and then I have a digital elevation model, so I know exactly how high each of the points on the glacier are, then I can extrapolate my measurements from where I measured to like much higher up or much lower down. And that's what I can put in a computer model then. So what we found out, what is really important in terms of the total energy that you get for the glacier melt is how reflective is your surface. And the reflectivity of a surface is called albedo. So snow reflects sometimes almost up to 100% of the incoming radiation. This is why you have to put ski goggles on when you're skiing, because it reflects all the solar radiation back. If you see my students there, they're wearing black jackets. Almost nothing is reflected. So if you are in a cold region and you're really cold, you look at a black rock to sit on, because that actually heats up quicker than the white rock, even though both rocks are in the same temperature environment, but one is actually reflecting more solar energy than the other. So what you can see here, glacier ice can be clean or can have some dirt on it, and dirt is usually not a word that scientists use, but I'm liberal here. Dirt means sediment, usually, and it also means some organic matter. But you can actually see snow reflects a lot more than glacier ice. So therefore, if that snow line is retreating, that ice is melting a lot faster than the snow. So when the glaciers are melting back, there is like what we call a positive feedback. The melt starts to become bigger, the snow line creeps up. Because the albedo is lower, it reflects less, and it will actually melt more. So all these factors we can actually put in a computer model. And so there's a lot of different factors, but eventually what you have is the short wave radiation, long wave radiation, and then these temperature factors, and you can calculate what the melt is. And I did that for a particular glacier on, most of you know where Columbia Icefield is. There is an ice field that is in BC that's called Clemens Icefield. It's just as big, as about 300 square kilometers. One of the glaciers there, I did a lot of research. The glacier is about 8 kilometers long. And I calculated what the melt is in, for example, early melt season and late melt season. So I think, are there 2 people working on this? So what you see here is maps where I calculated the melt, for example, in the early melt season, middle of June, and then the late melt season, 1st of August. The red area in the middle of June is only maybe 4 centimeters at the maximum that it's melting per day. The red area on the right, when it's late in the melt season, is 12 centimeters a day that it's melting. Now, the good thing about computer models, you can then turn the knobs a little bit, and you can actually say, okay, what if I switch this on or off? What I cannot do in real life, because for glaciers to do that, you have to wait 100 years and I'd be dead. And I can say in my grave I was right, but clearly as a scientist, you kind of want to be right or wrong when you're alive, and when you're wrong, you just kind of move on and do the next question. So what I did at the bottom there is, like, for the first time ever, I calculated what the radiation from the valley walls were and what kind of effect does that have locally on that one particular location and for the entire glacier. And I also switched on and off the strong wind. Often when you walk in the summer up to a glacier, you feel like a cold, strong wind. Now that strong wind is only really strong when the glaciers are big. When they get smaller, the wind is getting less. So to project how much water we get in the rivers in the future, how much the sea level is going to rise, we cannot assume exactly the same processes that are going on right now. So you have to kind of experiment with, okay, if in the future these glaciers are breaking up in smaller pieces, maybe the wind is not as fast. So then you turn that off. Now I have a computer model where you can actually see how much of a difference that makes over the entire glacier. So for the entire glacier, this particular example was a 10% increase in melt when you actually have strong wind or not strong wind. And nobody else had done that before. Now, other people make these types of models too. This is my particular model where I also had some utility. So I basically calculated how much water is going into the river. This is just streaming into the upper Columbia River Basin. It's millions of cubic meters of water each year. And all the glaciers that are feeding into that entire river basin feed in the late summer months, so like July, August, where you don't have a lot of rain, not even in BC. That about a quarter of the water in the rivers that high up in these drainage basins is from glacier melt. So you can imagine if these glaciers are gone, these river levels will be 25% lower. Now, colleagues of mine actually do that for glaciers all around the world. So they have similar models, actually better models than mine. And they also like incorporate some of the ice flow, and then you can first model what you know happened from the past. So this is, I think, between 1985 and 2015. Yeah, 1985 to 2015. So we know what happened because we have seen this. Then you increase the validity of your model, and then you can experiment and say, what if it was half a degree warmer? What if it were half a degree cooler? And then with that, you can actually do calculations with projected climate scenarios into the future. Like one scenario is where we're keeping to the Paris Agreement, for example. So with the Paris Agreement, worldwide, most countries signed it now. We want to have a global average temperature increase below 2 degrees, okay? That's one particular scenario. But if we're not that good, if we're actually like continuing on the path that we're now, we may have a 4 degrees increase. So then with these models, we can then see, calculate how much the sea level is going to rise. So clearly, there's a lot of different factors that actually are contributing to climate change and climate variability. Some of these factors are changing over really long time periods. You don't have a mountain popping up in a couple of 100 years or a couple of 1,000 years even. But there's a number of factors that can change a little faster and that are really important for ice sheet growth and glacier changes, and these are called the radiative forcings. Now, one of these is the sun, and the sun really hasn't really fluctuated that much over time. One of these is how far we are from the sun. Well, we are in an orbit, and that orbit changes over periods of like 40,000 and 100,000 years. So really, in 100 years' time, we don't have an increase or a decrease of that forcing. Where we do have increases and decreases of forcings is if you change the glaciers, so the reflection of the Earth's surface is different, or if you change the atmospheric composition. So the atmosphere around us gets changed, for example, by volcanic eruptions. Generally, volcanic eruptions only change the atmosphere for about 2 years, not for a longer time period. But clearly, we also have an influence on the atmospheric composition. Anthropogenic emissions. So these are basically the greenhouse gases. So we know from the ice cores, the graph on the left is an ice core from Antarctica from the last 650,000 years. You can see the natural variability of two of the greenhouse gases, CO2 and methane. And we can actually see that on the left side is the present. We can see both of these go off the chart. And we can then compare how much greenhouse gases do we have in the atmosphere right now compared to the natural variability. So naturally, this is actually over the last 15 million years, the maximum amount of CO2 in the atmosphere was about 290 parts per million. Now we have it over 400 parts per million. So what we're doing in the climate system, we're turning up this dial. And the climate system has dials and switches. So the dial is basically your thermostat. If you turn up the thermostat in the house to 20, it's going to be 20 degrees. But if you have some crazy cats in the house that switch on when it's 18 degrees, and you're a cat lady, and you're like, there's hundreds of cats running around with 18 degrees, you may have dialed your dial to 20, but because the cats are running, it now gets 25 degrees. Now this is what we're doing right now with the dial. We dial the above the natural variability, and there's a couple of switches that we may hit or have already hit. And one of these switches is in the ocean current circulation. So ocean currents can slow down or speed up, and the Gulf Stream brings some warm air to the northern hemisphere. This is why you can grow wine in France, for example, and at the same latitude as Lethbridge. But that could be a switch that, when you switch that off, suddenly the climate changes a lot quicker than if you just have these dials. So that's why it's important to actually look at the natural and the anthropogenic variability of the climate. If we actually look at the right graph here, all the natural causes of the climate change over the past hundreds of years haven't really changed much. They kind of go up and down a little bit according to mostly what the solar radiation is doing. But the black line is what we observe in terms of temperature. And the only way in which we can actually get that is with the greenhouse gases that humans actually put in the atmosphere. So it's absolutely certain that humans are the major cause of the most recent climate change and the speed of that climate change. So if we say global warming, it doesn't mean that every single part of the Earth is warming with the same amount. So if you take the last 10 years, 2008 to 2018, you compare the average temperature over that period to the average temperature over the last century, then on average it's 0.75 degrees Celsius warmer. But what you can see is in the Arctic region, it's more than 4 degrees warmer in some areas. You can also see some blobs in mostly ocean regions where the temperature has not really changed that much, or it has even become a little bit cooler. If we add everything up, though, on average, it's warmer. And when it's on average warmer, some of the other processes are speeding up too. So what we want to do in terms of keeping the glaciers healthy and keeping the entire Earth healthy so that we don't have climate refugees, for example, we don't have too many species dying off. We have the climate agreements that actually set what we want is not have higher increase, another increase not higher than about 1.5 to 2 degrees. That is reasonable given if we do our best. But if we don't do our best in terms of reducing greenhouse gas emissions, we will probably get 4 degrees increase by 2100, by the end of this century. Now, precipitation is also a driver of glacier change. Okay. And rain and snowfall over the world have also changed over time. And again, they haven't really changed in a spatially even way. Some parts have become drier, some parts have become wetter. Now, to bring all of this back to glaciers, we see some glaciers shrink, as almost a direct result of climate change. The temperature increase in the Canadian Rockies has most glaciers shrinking by about 20 to 30 meters a year. So they get shorter by 20 or 30 meters a year, and they get thinner by about 4 meters a year. So most of the glaciers in the Canadian Rockies, we give maybe another 50 years, and then they'll be gone. Okay, so drier or warmer climate, so either less snowfall or warmer temperatures, or both. Okay, so that would be a retreat. So this particular glacier retreated about more than a kilometer since 1850. And again, what you see here, when glaciers retreat, sometimes they have these proglacial lakes in front of them. When they're resting in these lakes, there's Iceberg Lake, for example, in Glacier National Park. Now, glaciers also get thinner over time, so we can actually see that in the field. This is an image from the Himalayas, the Indian Himalayas, where we're standing on the present glacier surface. And what you see is that the past glacier surface of the last ice, the Little Ice Age, so 1850, is towering about 200 meters above us. So this glacier has become 200 meters thinner than it was. Now, clearly, we don't have to go in the field to do this. We can actually measure this also with satellite images, and we can actually measure of almost all the glaciers in the world how much thinner they actually became. So then we have a budget, and we can actually see how much of that water run off to the sea. So if you actually look in the world, the amount of melt, the amount of mass loss, like globally, is dependent on how much area of glaciers there are in a certain region and what the climate did. So what you see here is each of these circles is a particular region with glaciers. The bigger the red circle, the larger the mass loss. So most of the big red circles are in the Arctic regions, and that's clearly as a response to like that increase of 4 degrees of temperature. There's also a rather large circle in the Himalayas that's called the third pole. So that's the third largest region with glaciers. And what is really important in terms of mass loss is also whether the glaciers are ending on land or whether some of those are ending in the ocean. Because when you end in the ocean temperature also goes up, and it melts part of these floating ice tongues, calving ice tongues. So that's why there is a spatial variability here. And you can see New Zealand and like Central America haven't really lost that much ice. Actually, the European Alps also not that much, because there's actually not a lot of glacier area in these regions. Now, you've all seen newspaper clippings like these. Well, there's this one glacier that's advancing, or there's this particular region, for example, Norway or New Zealand, where maybe the glacier retreat is not going as fast as in other regions. So what I'll explain in most of the rest of this talk is how can you actually figure out what this one particular glacier is doing? Is that still in response to climate change? Is it a regional change, or is it just like a local glacier that's actually like doing a little bit of a weird thing by itself? So why do some glaciers not retreat when all the other glaciers around it retreat? And what are the wild cards in the glacier and sea level rise predictions? So if we have some of these odd glaciers, do we need to incorporate those in our predictions, or do we actually need to eliminate those from our predictions because they're just doing their own thing? So clearly, differences in climate in response to climate are first of all reflecting differences in the climate drivers. So you saw that map of the temperature increase. Well, some regions have increased more, some regions have more precipitation, less precipitation. So this is why regions like New Zealand and Iceland and Norway, if you increase the temperature, you usually also have a little bit more snowfall. So if that snowfall is so much more, bringing so much more accumulation on the glacier than the extra melt, then the glacier may still grow as a response of an increase of temperature, right? Because it's both about precipitation and temperature, not just temperature. So that's why these regions, they're kind of easy to explain. Now, there's also changes in cloudiness. If it's warmer, there's more clouds, and especially when there's clouds overnight, we actually know that the Greenland ice sheet has started to melt more because it's actually cloudier, not because it's actually sunnier, but it's cloudier. And there's more long-wave radiation that is actually like heating up that lower atmosphere, for example. Now, with cloudiness also comes fog sometimes, and that's one of the things that I study that I'm not talking about this time. But if you're interested, you can talk to me after what that actually means for glaciers in the Arctic. Ocean temperatures have gone up, and I'll actually show some examples of how individual glaciers respond to that. Now then there's individual glaciers. All individual glaciers have what we call a response time. So if you have one freak year with a lot of snow, or one freak summer with a really high temperature, no glacier responds immediately to that because it first has to redistribute its mass, and it's quite a large body, and it's the same as if you, for example, put a turkey in your oven and you turn on the oven and you've had it on for half an hour. The center of the turkey is still frozen. The outside is not frozen. So sometimes it takes some time for that whole turkey to be equal temperature. That's the same thing with glaciers too. It takes some time. Now, how much time? In the Canadian Rockies, some glaciers take 10 years, other glaciers take about 100 years. That also means that these glaciers are never really in equilibrium with the climate that we have right now. They're always adjusting to climate that is slightly before. This is why different glacier sizes respond in different ways. So small glaciers respond faster than big glaciers. Now, if you have shrinking glaciers, the albedo goes down, but also they retreat to higher elevations. So some of these glaciers are now in the shadow all the time of this mountain range, and they maybe stop retreating. At the same time, there's lots of rocks that fall on it that insulate the glacier from more heating, and they may not retreat as fast as they used to be before they were retreated so much. Then we have the albedo issue that I already talked about, so like a accelerated retreat if you have more and more and more snow disappearing because the glacier surface becomes less reflective, so like really much faster melt. This is also what happened in the last ice age. We had a really fast actually melt, much faster retreat than advance of glaciers. Then I'll give you 3 examples of individual glaciers that actually may do different things. So one example is about surface debris. So clearly glaciers are in mountains. Some of these mountain ranges like, have rocks falling on the glacier, but we also have had forest fires. Forest fires actually bring soot, black carbon, onto the glacier surface, making the glacier surface darker. So these factors also play a role in the response of these glaciers to climate change. Volcanic ash, there's volcanoes and glaciers in certain regions. So I'll show you a little bit what was going on because of these factors. So this is the Greenland ice sheet. Usually the Greenland ice sheet still had the high regions that were completely dry snow, did not have any melt. For the first time ever in 2012, we actually had glacier melt going on. At the same time, the albedo of the Greenland ice sheet has gone down by about 15% in certain regions, by about 50% in other regions. And this is because of partly the Canadian forest fires too, that actually brought some of that black carbon onto the glacier surface. But some of that is actually just the dust blowing around and other organic materials. Now, the interesting thing about sediments that fall on glaciers, if you have a really thin layer of sediment, it increases the melt because it heightens the albedo and then it increases the melt. But when that sediment layer is more than 2 centimeters thick, it insulates the ice from underneath. So what you see here is a variability of images where some of them have like big rocks that are now glacier tables, for example. So they have a small little pillar that eventually they slide off the pillar. So dependent on the sediment thickness, first it can increase the melt, and then it decreases the melt when that sediment layer is thicker. Now, certain regions that are really high mountain regions, like the Himalayas, the Karakoram, the Andes, have so much like surface debris on them that they're actually not really melting down anymore in the lower regions that have a lot of sediment, like a lot of rockfall on them. They're actually only melting in the higher, what is actually the accumulation zone. So they're not retreating as fast as some glaciers that are not in the high mountain regions that don't have this cover of sediment. So clearly in Iceland we have coexistence of ice and fire, so we have volcanoes and glaciers. If a volcano erupts, you have tephra, or volcanic ash, that actually spreads over the glacier. Now, close to that eruption, that ash can be 2 meters thick, but further away, it can be really thin. So close to that volcanic eruption, you have a decrease of melt from the surface melt, and further away, you may have an increase of melt. So you have a local variability. At the same time, of course, these volcanoes melt these glaciers from the bottom, like really fast sometimes. So sometimes we have really catastrophic events like rock falls, and I've published a couple of papers. This is a rock slide. There's about a quarter of the size of Frank's slide, so we still see blocks here that are maybe 25, like they're as higher than this particular room. And that falls on a glacier, and that covers the glacier, and you come back after 10 years, and that area is now 30 meters higher than the surrounding glacier because it insulated that the particular part of the glacier from melt. Sometimes we have big earthquakes, you know, in the Himalayas again, or in Alaska. After a big earthquake, there's often these big rock slides over these glaciers, and some of these glaciers then start to flow a little bit faster or melt a little bit slower. So that's individual glaciers that are affected by some of these rock slides. So here the rock slide debris is between 2 and 30 meters thick, so it actually insulates the glacier from melting. We also have some organic material. There's snow algae or like watermelon algae that actually grow on these glaciers that also darken the glacier surface. And these snow algae, they actually like kind of slightly longer melt periods. So we have more algae on these glaciers and more organic material on these glaciers, and it makes these glacier surfaces darker. So sometimes it's blood red when you actually see some of these areas. We didn't slaughter any animals on this glacier, okay? And then we have these glaciers that end in oceans or glaciers that end in lakes, so tidewater and calving glaciers. So tidewater and calving glaciers, they have, okay, thank you. They sometimes have a big floating tongue, and the warm ocean currents can go underneath the tongue and melt the tongue from below. So these glaciers don't only melt from above, but also from below. And they can carve off these really big icebergs. So that's an additional factor. And when you actually look at Greenland, Greenland has been affected by this, and these ocean currents are not always in the same location all the time. So first, southeast Greenland was melting back really fast. There's about 200 tidewater glaciers that are wider than 2 kilometers that are draining from the Greenland ice sheet. And these tidewater glaciers in southeast Greenland started to melt really fast in 2000 to 2005. Then they didn't melt so fast, and then suddenly in the northwest they started to melt really fast. If you look at the ocean temperature curves, you can actually see in these particular years there was a really warm means it's only 2 degrees warmer. So if you go from an ocean temperature from 0 to +2, that's really important for the glacier melt. Okay, so don't think you can swim in these oceans. That's not how warm these currents are. But these glaciers, they're swimming in a hot bath suddenly. For them, a hot bath. So they melt back a lot faster. So regionally, you see differences going on over like the first 5 years, there's more melt in this region. The next 5 years, there's more melt in that region. So there's spatial differences because there's spatial differences in the drivers. And the driver here is the ocean temperature that is melting in. I don't think this works at all, so maybe I should just say next, okay? So another thing that tidewater glaciers have, they have kind of an internal clock almost. They advance often over hundreds of years because they just got thicker and their floating tongue will then push forward. And then they actually like push forward like a little ridge of sediment, and then often they get stuck in the end of the fjord. There's like a bit of a bedrock ridge, and they get stuck there. Now, when that glacier melts a little bit, it can float, and then it gets detached from that, like the bedrock sill that was at the beginning of the fjord, and then they actually retreat really fast. Over some tens of years, they can retreat tens or hundreds of kilometers. So really slow, long advance, really fast retreat. Now, in some of these phases, these glaciers are more sensitive to what the climate is doing than in some of the other phases. So when they're advancing, they're reasonably sensitive to the climate change. But when they're retreating, they retreat into deeper water, and they calve off icebergs until they're in the stable position again. And no matter really, like if you have a little cooler climate, it won't actually stop that retreat. So it's like an internal kind of clock. And this particular glacier can do a different thing than the neighboring glacier. Okay, so that's why some glaciers are advancing and other glaciers are retreating, and they're individual cycles. Some glaciers are even odder, and we call them surging glaciers. Now, most glaciers, even these tidewater glaciers, the flow speed is fairly constant over time. But surging glaciers, they have an internal clock where they sometimes flow way too slow to redistribute their mass, and then they suddenly break through, and then they may advance 9 kilometers in 9 months or 10 kilometers in several months, and they destroy everything in front of them, like houses. The Alaska pipeline is in a region where this happens. So they have a very long, very quiescent phase where they're flowing too slow, and then a short surge. And the short surge can be several months, but it can also sometimes be 10 years. So quiescence is much longer, is more like 100 years, where it flows really slow. Now, this glacier can do that, and not that glacier. And they have their internal clocks. So over the long time scale, these glaciers are still getting larger or smaller, but because they have this internal, like, oh, I now need to advance, I break through my previous restriction and outflow, and then they advance really fast. And sometimes that goes with glacier hazards too. So if you have a tidewater glacier that is in a surge, it will produce a lot of icebergs suddenly. So these particular glaciers, if you, I drew a graph here where you see the flow speed in meters per day of a surge-type glacier that is in Alaska, for example. So you see about 20-year period where it's flowing about 1 meter a day, and then suddenly for 2 years really fast. And it's kind of an internal clock that is fairly regular. Now there's another glacier in, for example, Svalbard, which is if you go from the northern tip of Norway to the North Pole, you get a group of islands. It's in the Arctic region. There's a surging glacier there in the orange line that has a longer quiescent period, and also, but still like an increase in flow and a decrease in flow, and a long quiescent period. When you have that newspaper clipping that says this one particular glacier is advancing, sometimes that one particular glacier is a surging glacier, okay? So why are surging glaciers also important? Some of the ice streams that are draining from the big ice sheets also have long periods of fast flow and then suddenly slow down. So I actually drew that curve off the chart here because the long period of fast flow is longer than my timeline in the bottom, and then it's suddenly shut down and now it's flowing really slow. So to understand that, we need to understand the response to climate change. And I mentioned earlier the fastest flowing, permanently fast flowing glacier in the world. That's kind of where the curve is. This is about 16 kilometers a year. And the last little bit, in the last 10 years, that glacier has started to speed up because if you have more meltwater on top of the glacier, it will actually drain into these holes, and then it will lubricate the bed so that the glacier can flow faster. So some glaciers in the world have started to flow faster because of the higher meltwater rates, especially in Greenland, in the regions. Okay. So fortunately, so there's about 200,000 glaciers in the world. Only about 1% of those are surge type, and we know which ones are surge type. We cannot predict exactly when they're going to advance, but we can easily see in certain regions where these are surge type glaciers, we can actually eliminate those from some of the direct climate responses. So what you see here, on this one, I want you to toggle forth and back, because there's like a map here. There's green and red. There's the worst colors for the colorblind. But hopefully most of you will see differences. So the red is kind of in the later period where there's a lot of retreat. There's one particular surge-type glacier here that is green in the earlier period. And if you actually include that particular glacier in the regional change in the regional length retreat of these glaciers, then it looks like regionally the length retreat was suddenly 3 times bigger. But if you exclude that glacier, that one glacier from like tens of glaciers that I'm measuring there, then the retreat only increased by 2 times, right? So that one particular glacier that is surging makes a big difference. So as glaciologists, we always need to see regionally, is this retreat partly because of these individual behaviors of surges or tidewater movement, or are some glaciers debris covered? Okay, now I got it. So how do we eliminate some of these glaciers from the record? So we don't eliminate them, but we actually like study them in a different way because they have an internal clock. So all these behaviors only last for a certain amount of years. So if I look at a region and if I look at a difference over 50 years, then I can include all these glaciers. But if I look over a difference in 5 years, so I'm measuring the length retreat from 1980 to 1985, then if there's one surging glacier, that will actually make a big difference. So I always need to average over the longer timescales because all glaciers, even the surging glaciers, the tidewater glaciers, the debris-covered glaciers, they still respond to the longer-term climate change. Okay? So on this graph, I have, for my colleagues, like summarized all of these different things together and told them, okay, so if you want to take into account this particular region, glaciers doing this, you have to average over at least this number of years. So now, this is actually an image that some of you may remember. It actually came out a couple of years ago. It was all over the news and all over the internet. This particular glacier, you see in 1918, I think 1914 and 2014, from the same vintage point with like a little bit more modern boat, but this particular glacier has retreated a lot. But what we know as glaciologists, not only did this retreat because of climate change, but it's also a tidewater glacier and it also happens to be a surging glacier. So maybe that retreat was partly because of the retreat, like what happens in the quiescent phase of the surge cycle, and partly because of climate change. So as glaciologists, we always have to like make sure that we know what system we're actually like looking at. So how are the glaciers doing in the Canadian Rockies? Well, in the last 100 years, we've lost about 25% of the glacier area. So they used to be like bigger. Glacier National Park in the next 25 years will have no glaciers anymore, or even shorter. In the Canadian Arctic, it's been going even faster. Oh, sorry, there's another one first. So that was in the last 100 years. What will happen in the next 100 years? Now only 20 years. By 2100, the volume of all the glaciers in the Canadian Rockies will have decreased by about 70%. So this is what we do with these computer models. We know what the climate's doing. We know how the glaciers are responding. So we will still have some glaciers left, but only about 30% of the glacier volume that we have now. And that is important for how much water is going into the rivers. Because right now, if you have a big glacier and you start to melt it, that whole area can melt. So first, you have an increase in your river flow. But then that glacier gets smaller and smaller and smaller and smaller, so the area that it can melt is also getting smaller. Once that's so small, it will actually then be beyond the peak flow. So increases in river runoff are only happening in the beginning when glaciers are melting. But when the glaciers are so small, like in 50 years' time, we won't have as much water in the rivers anymore because these glaciers are so small, they don't actually have the area to melt. So in some regions, like here in Alberta, we are already beyond that peak melt. So even if we crank up the temperature and we let the glaciers melt more, there's actually still less and less water going into these rivers. But there's other regions like the Himalaya where there's millions of people reliant on the glacier melt where they're not at the peak melt yet. So they first get more water in the rivers and then less water in the rivers once these glaciers have shrunk to like smaller sizes. In the Arctic, so I'm still not at the Arctic, I'm still on the Rockies. I really like the Arctic, so. So if the local yearly temperature, remember the Paris Agreement? We want to have a temperature increase like 1.5 degrees at the maximum, but we're probably not going to make that. So if we actually make the 1.5 degrees, we will actually lose all the glaciers south of 56 degrees north. And that's kind of if you go from Edmonton, like straight west, all the glaciers south of that. So that's actually the glaciers in Banff and Jasper National Park. They will be gone with that amount of climate change. Now we have the Arctic. So the Canadian Arctic ice caps, because of the temperature increase that has been like 2 or 3 times the global average temperature increase, they have been melting a lot faster, and a lot of the Canadian Arctic glaciers also end in the oceans. So they also had that extra melt from the ocean water. So some regions have already lost 50% of the glacier area. And in terms of glaciers outside the 2 ice sheets, the Canadian Arctic has been one of the regions that has contributed the most to like the present sea level rise. Oh, okay. So now let's bring this back to why glaciers are important. Well, we have a lot of fresh water in these glaciers, and some of my students actually can drink the fresh water. We never have a water shortage on the glaciers as long as somebody is not paying upstream from them. So we have strict rules about that. But this water eventually, the water that you see the student on the left take, that water eventually runs off into the upper Columbia River Basin, and that ends up in Seattle, in the rivers like in the Pacific Ocean. Okay, so in fairly small glaciers in the Canadian Rockies, if you look at Alberta, and we look at where all the rivers exit Alberta, that's mostly in Saskatchewan, only about 6%, 6% of the water is from glacier melt, because like on the way it picked up like snow melt, and it picked up some groundwater, and it picked up a lot of precipitation. But the closer you are to the glacier source, the higher the percentage of the water that comes from the glacier. So in Banff, in the late summer, we have about 55-60% of the water in the rivers that comes from glaciers. And we've already seen that some of the glacier melt has now occurred sooner in the spring is quite early. The season of the melt is longer, and some of the glaciers have already decreased in size so much so that eventually we'll have a loss of 70% of that water that's in the rivers right now. That's in the prairie rivers. Now, what's the global sea level doing? We know that the global mean sea level is rising. Over the last 100 years, it's risen about 25 centimeters, but it's faster and faster and faster and faster. And how much will it accelerate further? So usually we do these calculations to the end of this century. So how much is it going to rise? And I never stopped teaching, so this was the last Halloween, and I was actually dressed up as Miss Sea Level Rise, where I put for 1.5 degrees, here's your answer already. I'll give some more detailed answer in the next slide, but it's either 1 meter or 4 meters globally. So what we usually do as scientists, every 4 or 5 years, we collect all the scientific data and put it in a digestible package, which is called the IPCC report. And those reports are the state-of-the-art kind of information. But the last report was 2014, and we have had a lot of new research. So in that IPCC report, we still actually had averages of 0.5 meter to 1 meter. And I was just at a conference last week in the Netherlands where they're building dikes. They're 2/3 of the Netherlands is below sea level already. So when you want to increase and strengthen your dike, they've always taken into account, well, it's not going to be more than 1 meter. Now suddenly in the Netherlands, they have to take into account that perhaps it's going to be 2 meters. Because we're actually not doing as good as the best scenario in the IPCC reports. We're actually doing a lot worse than that. So the global sea level rise, what you see in the red curve is the most likely kind of sea level rise is still between about 0.5 meter and 1 meter, but possibly up to 2 meters. And that's when no crazy things will happen with the Antarctic ice sheet. Now, of that, Now, in the last 100 years, it was mostly all the local glaciers that were melting, but now both the Greenland ice sheet and the Antarctic ice sheet have started to melt too, and they contribute more and more and more. And that's why we're going to have 1 to 2 meters more of sea level rise. But there's also part of the Antarctic ice sheet that is actually like partly floating on the ocean, and if that collapses, then the sea level rise can potentially be 4 meters. But the problem with IPCC reports and anything that you have to do for politicians, it's very conservative. In fact, like scientists are really conservative. So we cannot actually put that 4 meters in our reports because we don't know if this collapse is going to happen in 50 years or 100 years. And if we don't know for sure, we cannot put it in the reports. But it's possible that it can happen in 50 years and that we have more than these 2 meters. So if you look at the Antarctic ice sheet, there's a mountain range that separates a part of the ice sheet that's resting on land, and the West Antarctic ice sheet is actually like mostly floating in the ocean. If the ocean level is going to rise, it lifts that glacier off the bed, and these like some of these ice shelves are completely collapsing, and some of the glacier ice that is on the land behind it will move faster. So this entire area can become unstable, and that's where you can have projections of sea level rise that are more than the 2 meters. Okay. Now, we're at 925 meters above sea level. We don't really care that much, but there's maybe a reason why I moved here from my half a meter below sea level. Although the Netherlands is pretty good at building the dikes. But they were joking, like maybe we have to learn more German because we may have to like move inland, and like the Dutch may become climate refugees. And the Dutch are rich and they're like good engineers and they can like invest in all these things. But there's a lot of islands in the South Pacific, there's Bangladesh, there's a lot of other countries where the mobility of the people and the investment kind of capacity is not that large. So we will have, there's millions of people that live within 1 meter of sea level rise. We're going to have at least 1 meter of sea level rise. Here. So on the left, you can't read it because it's in Dutch too, but in high school I wrote a little report, and it was based on like 2 or 3 books that I read, and this is in 1987 in my last year of high school. And I called this report the Ice Age Jump. So basically it was about the first kind of reports came out about the human influence on the climate. In 1987, as a high school kid, I knew this. Apparently it takes us 30 years to now realize, well, maybe humans have an influence on the climate. We knew this, I mean, interested people that actually like know something about science, knew this 30 years ago. And even governments knew this 30 years ago. So on the right, what you see is glaciers and ice sheets and sea level effect of CO2-induced climate change. This is a report partly for the US EPA in 1984, I think 1984, where they were investigating that. So they knew 30 years ago already what was going on, how like the greenhouse gases were actually influencing these glaciers. So why does it take 30 or 35 years? Well, there's a lot of people that are not happy about reducing our greenhouse gas emissions, and it's not about individuals not believing this, it's about groups of people telling misinformation to people. So I'm a climate expert, okay, a climate and a glacier expert. So if you want any information, don't listen to your like supermarket checkout person or to your doctor or to your dentist. They're experts in their field, right? But for climate, listen to the climate experts. So in summary, we are losing ice. My uncle actually took this picture a while ago in the summer. We are losing glaciers. They're sold out. Eventually, we won't have anything left to actually You can put them all on, actually. So glaciers are beautiful and they're intriguing. Hopefully I've shown you some pictures to show that. Glaciers are shrinking in response to global warming. Shrinking glaciers eventually means less water in our rivers because the glaciers are gone. Faster melting means faster sea level rise, and that's kind of the projection is at least half meter to a meter, but perhaps 2 meters. Humans contribute significantly to climate change, and I thank you for your attention.
This is our final Public Professor episode for the 2018-19 season, but we will be back next year with another great lineup.